You ever notice how some of the simplest questions, like how does light work, lead to the most mind-boggling answers?
It's so true.
Well, get ready to dive deep into that very question. We're cracking open Feynman's lectures on physics,
Hmm.
specifically his work on optics.
Oh, Feynman, always a good time.
Now, before anyone starts sweating about physics exams, I promise this is going to be fun. It's about understanding, like really understanding how we see the world around us.
Yeah, it's like peeking behind the curtain of reality.
Exactly. And trust me, things are about to get kind of trippy.
You have no idea.
So at the heart of it all is this mind-blowing idea that light always takes the path of least time. It's like it's got this internal GPS always calculating the fastest route.
It's wild, right?
Okay, so to wrap our heads around this whole light speed strategy, let's zoom out for a sec. When we talk about light, we usually think of like the colors of the rainbow, right?
Right.
But that's just a tiny sliver of a much bigger picture, isn't it?
Yeah, it's like we're looking at one key on a piano when there are, like, a zillion other keys we're not even hearing.
Okay, I like that analogy.
What we see as visible light is just one tiny part of this massive spectrum of electromagnetic radiation.
So what other invisible notes are on this cosmic keyboard? Fill us in.
All right, so on one end, we've got these super long, low energy waves,
What?
like radio waves. Some of them are seriously huge, even longer than football fields. Can you believe it?
No way.
Yeah. And as we move to shorter wavelengths, higher energy, things start getting interesting. We hit microwaves, for popcorn and stuff. And then infrared, which we feel as heat.
It's like a spectrum from these giant mellow waves to these tiny, super intense ones.
Exactly. And the crazy thing is, each part of this electromagnetic spectrum interacts with matter in a different way.
Makes sense, I guess.
That's why we need different tools to study them. Like, you wouldn't use a microscope to look at a galaxy, right?
Who true?
We use telescopes for distant stars, X-rays, to see inside our bodies.
Yeah.
It all depends on the type of light or radiation we're dealing with.
Okay, that makes sense. So let's bring it back down to Earth a bit, or at least back to visible light. Even within that tiny sliver of the spectrum, there are these fascinating laws that govern how light behaves.
Oh, yeah.
Like when light hits a surface, it can either bounce off, which we call reflection.
Right, like a mirror.
Exactly.
Yeah.
Or it can bend as it passes through, which is refraction.
Like when you look through a glass of water and everything looks kind of distorted.
Exactly. It's like light is playing a cosmic game of billiards, bouncing off mirrors and tipping into prisms.
I like that.
And reflection seems pretty straightforward.
Yeah.
But refraction, the way light bends when it goes from, say, air to water, that had scientists stumped for ages.
Oh, yeah. For a long time, they couldn't figure it out.
Seriously. You'd think something as basic as light bending would have been figured out, like, a long time ago.
You'd think so, right? But it turns out it's a lot trickier than it looks.
Oh, I bet. So what made it so hard to crack? Tell me more. So how'd they finally crack the code of refraction? Was it like a eureka moment or something?
Well, it involved a bit of a need for speed, you could say.
A need for speed. Okay, now you've got me curious. What does that even mean when we're talking about light?
So back in the 17th century, there was this brilliant guy named Pierre de Fermat.
Okay, Fermat.
And he figured out that light doesn't always travel the shortest distance between 2 points, but it always takes the path that takes the least time.
Wait, so it's less about mileage and more about, like, beating the clock.
Precisely. It's all about optimization. Light's been a master of traffic avoidance since, well, forever.
I can relate to that,
Yeah.
especially during rush hour, am I right?
Haha, exactly. But light's been doing this on a cosmic scale for, well, forever.
So how does that apply to, like, light bending in water? I'm not quite seeing the connection.
Okay, so picture this.
Okay.
You're trying to get to a friend's house across a park. You could walk around the park the shortest distance, right?
Mm.
But what if cutting across the park diagonally, even though it's a longer distance, is actually faster because you're spending less time on the slower grass and more time on the faster sidewalk?
Oh, I see. So it's like minimizing the time spent in the slow zone, even if it means taking a slightly longer route overall.
Exactly. And that's basically what light does when it bends in water. You see, light travels slower in water than in air. So to minimize its travel time, a beam of light will actually bend as it enters the water, taking a slightly longer path through the air, but a shorter path through the denser, slower water.
So that bending, that refraction, it's all about speed optimization. Mind blown. It's amazing how a principle this simple can explain something that puzzled brilliant minds for centuries.
Right. But it doesn't stop there. This whole least time thing, it has some even weirder implications.
All right.
Like, did you know that we can still see the sun for a few minutes even after it's technically set below the horizon?
Wait, what? Seriously, I thought once the sun dips below the horizon, it's gone. How can we still see it?
It's actually an illusion. Our atmosphere is playing tricks on us.
Oh, interesting. I didn't know that.
Yeah, so the Earth's atmosphere isn't uniform. It's denser near the surface and gets thinner as you go higher. And remember, light slows down in denser mediums.
Right, like in water.
Exactly. So the light from the setting sun, it's being slowed down by the denser atmosphere near the horizon. And as it slows down, it bends. The light takes this curved path through the atmosphere to reach our eyes, even though we perceive it as a straight line.
That's wild. So we're seeing the sun where it appears to be, not where it actually is.
Precisely.
Wow, I never knew that.
And this bending of light in the atmosphere, it's the same reason you see those mirages on a hot road. The hot air near the ground is less dense, causing the light to bend and create the illusion of a reflecting pool of water.
Oh, wow. I always wondered about that. But that's all connected to light taking the path of least time.
It all comes back to Fermat's principle.
Wow.
Another cool thing is how this principle applies to the design of lenses and telescopes.
Oh, that makes sense. All those curved surfaces are designed to bend light in just the right way to, like, focus it, right?
Exactly. By carefully shaping lenses, whether it's for your eyeglasses or for something as powerful as the Hubble Space Telescope, we're essentially manipulating the path of least time for light rays, and that's how we get those crisp images, whether we're looking at tiny cells or distant galaxies.
Wow. Okay, so light is clearly a strategic traveler, but how does it know to take the fastest path? Does it have some kind of internal stopwatch and roadmap of the universe or something?
That's the real head scratcher, isn't it? It's like light has this sixth sense, this ability to scout out all the possible routes and pick the fastest one.
So how does it do that? Does it carry around like tiny maps and calculators?
Not quite. The secret lies in the fact that light doesn't just travel in straight lines like a laser beam. It also acts like a wave, spreading out and interfering with itself.
Okay, I'm picturing those ripples in a pond spreading out from a dropped pebble.
Perfect analogy. Now imagine those ripples hitting an obstacle, like a rock in the pond. What happens?
They bend around the rock, creating these cool interference patterns. I've seen that at the beach.
Exactly. Light does the same thing. It's constantly sending out these little feelers, these wavelets, exploring all the possible paths. And here's the key. The paths where those wavelets reinforce each other, those are the paths of least time.
So it's like a cosmic competition between all the possible paths, and the fastest one wins.
You got it. And get this. We can actually see this path exploration happening. Have you ever held two fingers really close together and looked at a light source through the gap?
Yeah, actually, I've done that before. You get these like fringes of color, right?
Exactly. That's it. That's called diffraction. And it's proof that light is exploring those paths around your fingers, interfering with itself to figure out the fastest route.
Whoa, I never realized that simple experiment was showing me something so fundamental about light.
It is. And hold on tight, because things get even weirder when we zoom into the quantum realm. At that level, light can act like both a wave and a particle, called a photon.
Okay, now we're going down the rabbit hole. Hit me with it.
So at the quantum level, we can't actually know for certain which path a single photon will take. It's like it travels all possible paths at the same time, but the paths with the least time are the ones that are most likely.
So even at the quantum level, this principle of least time still holds.
It seems that way. It's like light at its core is hardwired for efficiency, always finding the quickest route from point A to point B.
This whole deep dive has been mind-blowing. We've gone from reflections to quantum mechanics, and it all started with this idea of light taking the path of least time.
And we've only just scratched the surface.
That's the amazing thing about science, isn't it? Every answer leads to more questions. So, to everyone listening, next time you flip on a light or see a rainbow, think about the incredible journey those rays of light took. You might be surprised by what you discover.